Hello, I'm Darren Naviger, Principal TSC at NI. And in this presentation, I'm going to be talking about built-in LabVIEW debugging tools. Before I get started, though, I want to mention that this is another presentation in my series on LabVIEW troubleshooting. If you have not watched the other videos in this series, there's a couple more before this one. Definitely go check those out at bit.ly/dnatlv troubleshooting. In addition to there being recordings of these presentations, you will also find downloads for the slides and for the demos. The slide demos are particularly important because they are going to include a whole lot of links to additional resources related to the topics being described in this presentation and in the others as well. But for today, I'm going to be talking about tools that are built into the LabVIEW environment to help you troubleshoot LabVIEW code that is having problems. And the first tool that I'm going to talk about is the breakpoint. If you've ever had to debug LabVIEW code, you have probably used breakpoints. And most of the time when we use breakpoints, we are using them to pause LabVIEW execution at a particular point on the block diagram. And the most common place we place breakpoints is on wires. We want the code to pause as data is flowing from one node to another node. We want to pause in between those to be able to determine some sort of problem that's happening. But if you didn't know, you can also set breakpoints on nodes themselves and on diagrams. And so when you set a breakpoint on a node, your LabVIEW execution is going to pause once every wire has completed execution going to that node. If you set a breakpoint on a diagram, LabVIEW is going to pause before anything on that block diagram executes. But most of the time, we're setting breakpoints on wires. Now, if you've got a lot of breakpoints distributed through your LabVIEW code, you may want to use the breakpoint manager to try to manage what's going on with all those breakpoints. The breakpoint manager gives you a single window that lists all the breakpoints that are currently set in your code. You can do things like delete breakpoints or enable and disable breakpoints from the breakpoint manager. And there were several new features that were added to the breakpoint manager in LabVIEW 2020. So if you're using 2020 or later, you have access to these features. Specifically, these features are shown here. So there is a shortcut that allows you to select all the breakpoints in your code. So if you want to do something like delete them all or disable them all or something like that, you can use the select all breakpoints to do that. There are also some configuration options that let you sort of manage how things appear in the breakpoint manager window itself, like showing the titles of VIs instead of their VI file name. And then there are a couple of refresh options. So these options to refresh and to rebuild that you see there are typically going to be used when you've got a lot of things going on with dynamically called VIs or reentrant VIs or both, such as the case with something like Actor Framework. And you're going to want to use those menu options to be able to see, oh, there's some new reentrant VI instances that have been spawned and they have breakpoints in them, and you want those to appear in the list. And if something ever gets out of sync or you don't think things look right in the breakpoint manager, there's the option to rebuild, which is basically like closing and relaunching the breakpoint manager to rebuild the list that's shown there. So again, these are all new features in LabVIEW 2020. Check those out if you're using 2020 or later. Another tool that's related to breakpoints because it pauses your code is single stepping. So if you've never used these functions, these three buttons are going to appear in your block diagram toolbar when your LabVIEW code is executing. And they allow you to sort of have granular control over when the code is paused and at what levels you want it to be paused at. For example, if your code is paused, like if you've set a breakpoint, you can start stepping. And when you click the step functions, you have the option to step into sub-VIs so that you can now debug the code in the sub-VI and have things paused and things like that. You can also step over. So if you're paused at a sub-VI and you don't want to go into that sub-VI and have everything be paused, then you can step over it to move along execution on the current diagram. And the step out button lets you, if you're inside of a for loop or inside of a sub-VI and you are done debugging in there and you want to sort of go up to the next level, you can click the step out function button as well. So if you've never used the step functions when debugging in LabVIEW, they can sometimes be a little bit more efficient than, pausing at every node or using execution highlighting to make the code run slower. The step functions can sometimes make it easier to debug and be able to have control over when you go into and when you don't go into certain sub-VIs and structures and things like that. So along with breakpoints, probes are probably also the most commonly used debugging tool in a LabVIEW block diagram. So a regular probe is going to just show you the value of something going through a wire, but the LabVIEW editor allows you to create and use custom probes as well. A custom probe is a VI that you have written that will display in the probe window and sort of customize the appearance of what's being shown. For example, in this slide here, we have a custom probe of an array, but this custom probe isn't very interesting. It's still showing just the array of values. When custom probes can be really useful is when you write LabVIEW code to visualize the value in a wire better than just its raw value. Possibly one of the best examples of this is the VI reference custom probe. So on the left is what happens when you probe a VI reference with the generic probe, just like the built-in probe. And as you can see, you get back a U32 value that is completely worthless as far as, I guess it's not completely worthless because if you probe a null VI reference, you'll get a 0 there. So at least seeing a number there tells you something. It tells you that there was a legit VI reference that had been created at some point, but that's about all that it tells you. Contrast the generic probe on the left with the custom probe on the right. So this is a custom VI reference probe that ships with LabVIEW. So by default, when you probe a VI reference, you should see the picture on the right, not the picture on the left. And look how much more useful that is. What we do is we look at the VI reference inside the custom probe VI, and we can get you the VI's name and its path and what app instance it's running in. So the custom probe, this is a good example of a way to really illustrate how with LabVIEW code, you can have a probe that provides much more useful information than just the generic data type. Another very useful custom probe, and again, these are all shipped with LabVIEW. Everything in this presentation are things that are part of LabVIEW, is the conditional error probe. If you're probing an error wire, this probe is extremely useful because in addition to being able to view the value on the wire, you also have conditions that can pause the code. So you're basically turning your probe into a conditional breakpoint. You're saying, if an error passes through this wire, I want my code to pause. So the conditional error probe is one of the best troubleshooting tools we have for troubleshooting error conditions in our LabVIEW code. And possibly my favorite kind of probe is the history probe. So in LabVIEW 2019 and later, if you probe what I would call the standard LabVIEW data types, numerics, paths, strings, things like that, you have the option to create a history probe off of that type. And a history probe, in its simplest terms, will just display the value, every value that has flowed through the wire. So it's really useful when you're debugging situations where code is executing repetitively, like let's say in a loop, and things aren't going the way you expect. And it would be really handy to know what is every value that has passed through that particular wire. The history probe gives you that exact information. Now, I mentioned that the history probe ships with LabVIEW 2019 and later. If you're using LabVIEW 2018 or previous, you can still use history probes. You just have to go download them from ni.com. And I included the link here in the slides. And again, you're going to want to go to bit.ly/dnatlv troubleshooting to get all these links to be able to download these resources in the slides. All right, so now I'm going to switch over to a few demos related to probes. So the first thing I'm going to do is I'm going to write a random number strip chart VI, but I'm not going to use a strip chart. I'm just going to use a numeric. So if I just create my while loop here and just create an indicator off of the random number and add my wait function. So now I've got a random number generator VI. It's, I guess, not a strip chart. Now, let's say this is part of a much larger application, and let's say that I'm having a problem and I want to probe that wire. Well, by default, I'm going to just get the regular numeric probe. So this is the numeric probe that you see for the numeric data type. Now, there is a very little known feature in LabVIEW where you can specify that instead of this default probe, you want to use a control from the front panel as your probe. So for example, I could go probe this wire, and under custom probe, there is a controls menu. You've probably never used that menu option in your life. And look what I can do. I can do something interesting like making a meter be my probe instead of a numeric. Now, this may not seem very useful, and you're right. Having a meter that probes a numeric value is not terribly useful. but there is exactly one time where I have found this feature to be useful, and that is when I want to see a history of the value going through the wire with a graphical sort of representation. So what I do is I right-click on the wire and do custom probe controls, but I go to the graphs palette and I pick the waveform chart. Now I've got a probe that is a chart that is showing the history of the values that have gone through that wire. This is the only time I have found the controls pull right menu for probes to be useful, but I figured I'd mention it. Very easy way to get a chart that shows the history of values if you want to do that for your probe. But that was one little small thing I wanted to show. So something else that I wanted to show is the history probe. So here we have a queued message handler. This is the project template that ships with LabVIEW. And it is a very simple design. Hopefully you've seen some of my other presentations on design patterns. In fact, that was my first presentation for troubleshooting. So hopefully you're familiar with what a queued message handler is. The demo, the project template that ships with LabVIEW is very simple. It has a couple buttons and that's it. Well, let's say you have an application based on the queued message handler, but there's a problem with it, and you think the problem has to do with the order in which messages are coming into the message handling loop. This is where you can utilize history probes, like I talked about before. So I'm going to take the message string in the message handler, and I'm going to go to custom probe and choose history string. What this is going to do is this is going to give me a history of every value that has passed through that wire. Now, if I run the VI and use the queued message handler, you can see over here in the history probe, we have seen a history of every value that has flowed through that wire. Now that's pretty cool. An extremely useful debugging tool. There are history probes, like I said before, for all the basic data types, numeric, strings, Booleans, paths. Now let me bring up another example here. And that's the state machine. So here's another template that ships with LabVIEW. Again, I've discussed state machines in a previous presentation. And again, this one's very simple, just pops up dialogues when you click buttons. Now, let's say you have a problem with the state machine, and again, you think the ordering of your states is something that's causing the problem. Once again, we can right-click and we can go to custom probe and choose history, but look at the type, it's a U16, just a regular numeric U16 type. Now, when I run this code, if we look at the history probe, this is not nearly as useful as what we saw before, because these are just the numeric values of the state enum that's running our state machine. Wouldn't it be nice if we could have a history probe that showed us the history of those enum values in a way that's much more useful for visualization than just seeing the numeric values? Well, it turns out that it is extremely easy to create your own custom probe based on another custom probe. And we're going to do that right now. So I'm going to right-click on that state enum. I'm going to go to custom probe and I'm going to pick new. That's going to bring up the create new probe dialog. And what I'm going to do is I want to create a probe from an existing probe. Specifically, I'm going to find the history string probe, and I'm going to create a new probe from that and use that for my state machine enum probe. Let's call it demo state enum and click save. And we now have our own custom probe that's based on the state enum, and you can see, or based on the history probe for string. Just now it uses the enum type instead of the string type. So I'm going to need to make a few quick changes to this VI to make it a viable history probe for my state enum. First thing I'm going to do is I'm going to hide that control on the front panel so it's not getting in the way of my table. Then I'm going to come to the block diagram. Don't worry about what's going on here. This is the history probe code. It looks pretty complicated, but we don't need to understand most of that in order to make our change. All we need to do, remember, this probe was originally used with a string as the input type. So if I just use a format into string function to turn the enum into a string, that is all I need to do to make this probe work for my state machine enum. So I'm going to save this probe and I'm going to close it. Now, when I right click on that wire and do custom probe, check it out. My new custom probe is shown in the list. And when I click on it, I now have a probe that's for that enum. And when I run my code, we now see that that probe returns the enum values instead of the numeric values. So much more useful for debugging. And you saw it took me less than a minute to create that custom probe for that data type. So if you're troubleshooting a LabVIEW application and you have custom data types that you really need to probe and you want to have a better visualization than just whatever the default generic probe types are, this shows you how easy it is to take an existing custom probe and fit it to the needs of whatever specific data type that you have. All right, so moving on to my demo, I'm going to talk a little bit about highlight execution. So you've probably used highlight execution before. It's the little light bulb in the toolbar, and it lets you watch the values flow through the wires of your code. Now, I personally do not use highlight execution that much. I know a lot of LabVIEW programmers do. I have never found it to be particularly useful. And one of the reasons is because it's kind of slow, especially when working with large block diagrams. So I find that if I'm trying to use it, I'm kind of sitting around waiting for something interesting to happen. Well, I guess I'm giving the feature a second chance now because of something new that was added in LabVIEW 2019. There is a new feature called toggle execution highlighting that allows you to have the highlight execution on for only a part of the block diagram, and you get to define where that part is. And I'm going to demo that in a minute, but one other thing I do want to talk about is retain wire values. Retain wire values might possibly be the most useful debugging feature in LabVIEW, in my opinion. When you turn on retain wire values, every single wire on every single block diagram that's in memory, or that's open, I guess, is retained so that you can probe those wires after the VI has finished executing to see what the last value was that went through that wire. It's an incredibly useful debugging tool. It makes it so that you don't have to sort of sit and figure out from the beginning which wires you think you might need to probe while you're troubleshooting something. Retain wire values lets you kind of go back after the fact and see what the values were that went through certain wires. All right, so I'm going to bring up a VI to be able to demonstrate a couple of those features that I just talked about. Let me go ahead and close this project here and open a VI that I want to debug. So this is a VI that's doing some math, and I'm going to go ahead and run it. And let's say as I'm working in my code, I see something in one of these graphs that doesn't look the way I expect it to. So I need to go in and debug this VI. Now, I'm pretty sure that something is going wrong inside this for loop here. Now, I could turn on execution highlighting now, but when I run it, I would have to wait for the code to get into the for loop. And then once it was done, I would have to go turn off execution highlighting. These are things that I can now do. I can now define where I want the execution highlighting to run. So if I right click on any wire inside the for loop and do custom probe toggle execution highlighting, and then I do the same thing on a wire that's at the very end of that for loop. I'm also going to turn on retain wire values because there may be some other wire in this code that I want to probe. But now when I click the run arrow, watch what happens. Execution highlighting didn't turn on until we got into this for loop. Now execution highlighting is working. I'm seeing all the values flow through the wires of here. But once the for loop is done at this point right here, execution highlighting turns off and the rest of the diagram executes. So very useful way to just have execution highlighting on for a certain part of the diagram. And since I remembered to turn on retain wire values, I can now come in. I did a shift right click, by the way, to bring up the tools palette and pick the probe tool. Now I can come in and I can probe wires after the fact and see what the values were that went through them. Even though I didn't have those probes set up at the beginning, since I turned on retain wire values, I can see what the last values were that flowed through those wires. Extremely useful debugging tool. All right, so now I want to talk about suspend when called. This is one of the most interesting debugging features in LabVIEW that you've probably never heard about. So this is an option that you can configure on a sub-VI to make LabVIEW stop and pause execution when it gets to that sub-VI. And that may sound not that interesting. That's something that you could do with a breakpoint. But the interesting thing is you can start messing with that sub-VI and changing its inputs and changing and running it on its own in isolation to test things. And what's the most useful, you can actually define a sub-VI output that has nothing to do with how the sub-VI executed for when the main VI starts executing again. Not as cool to describe out loud as it is to actually demo. So let me switch over to a demo of this feature. All right, so I have this VI, main.vi, and as you can see, its block diagram is very simple. It is calling a sub VI that says sum. So presumably this VI is going to add two numbers, right? Let's try it out. 2 plus 3 is 5. Okay, so we know what that sub VI is doing. But let's say that that sub VI is doing something that we didn't expect. Let's say it's saying 2 plus 3 equals 6 or something equally as bad. So we need to debug that sub VI and figure out what the problem is. But we may want to play around with the sub VI with different inputs to see if it works sometimes with some values, but it doesn't work sometimes with other values. So what I'm going to do is I'm going to right click and choose sub VI node setup. And here is where I can configure suspend when called. So I'm going to click OK. Now I'm going to run this VI again, 2 plus 3. But when I run it, you can see the main VI is sitting waiting while the sub VI is sitting here paused. Now, what am I going to do now? Well, what I can do is I can play with this sub VI. So I can say, well, let me see. Does it work OK with 3 plus 3? Does it work OK with 4 plus 6? I can just play around with the inputs. And when I'm done playing with the VI, here's the really cool part. Let's say my code, I expected it to return a value of 20, but it wasn't. Well, I want the main VI to act as if the sub VI did return the value that I wanted. So I can actually type in a different value on the sub VI front panel that has nothing to do with its inputs. And when I click the return to caller button, it's going to return to the main VI and return the value that I specified, not the value that the sub VI generated. So again, you've probably never seen that feature before, but it's really, really handy when you're debugging. You may have a sub VI that doesn't work as you expect, or you may want to see how your main VI reacts to a sub VI output that it wouldn't normally generate. With suspend when called, it's a great way to troubleshoot those situations. So next up, I'm going to talk about the event inspector window. This is a really handy debugging tool when you're doing event-based programming in LabVIEW. So what you can do is you can right-click on an event structure and launch the event inspector window. And it will bring up a window that basically shows you a log of every event that has been fired, or I guess responded to by any active event structure in any of your VIs. But this is another one that's better to demo. I'm going to come back and I'm going to bring up my queued message handler project again. So here we have our main VI, and it's got this event structure in it. So what I'm going to do is I'm going to right click on the event structure and choose event inspector window. Now I'm going to run the main VI. And if we watch in the event log here, we'll see that every single thing that happens with this event structure, every event that it's registered for that fires, we see show up in the event log. Now that all seems pretty interesting. But another useful thing is that the event inspector window will show you events that are in the event queue. So events that it's expecting to handle but haven't been handled yet because it's busy with something else. So to demonstrate that, what I'm going to do is I'm going to add a slight delay to one of the cases in the event structure. So now whenever the do something button is clicked, we're going to also have this 500 millisecond wait. So now if I run the code again, if I spam the do something button, you would expect to see a whole bunch of events show up in the unhandled events list, right? Well, that's not what happens. When I spam the button, we see that only one unhandled event shows up in the list. In fact, I'm going to click the button, let's say about 10 times. And you can see that each one of those times we're sitting and we're waiting 500 milliseconds for those events to happen. Now, the reason this is happening is because of a configuration option in the event structure. If we right click and do edit events handled by this case, there's this checkbox that says lock panel until the event case completes. So basically what's happening here is the event structure isn't letting you fill the event queue with events because it is sitting and it's waiting for the current event to be processed before it unlocks the panel. If we uncheck that button and do the same thing again, now we start to see a whole bunch of events show up in the event queue because now the panel isn't locked and so other operations can take place. If you're seeing issues with event queues getting flooded or the opposite, you're not seeing events queue up that you think should, take a look at that checkbox, the locking of the front panel, because that can sometimes be the cause of strange UI event queuing type problems that you might see in your code. All right, so now I want to talk about Debug Write.vim. This is a debugging tool that you will not find in the palettes or in QuickDrop in regular LabVIEW because this is a hidden gem. So if you've never heard of hidden gems are VIs that ship with LabVIEW but are not officially documented and in QuickDrop and on the palettes, but they're still very useful for certain use cases. I have a presentation that I've given on all the really great hidden gems that ship with LabVIEW. You can get that at ni.com/hidden gems, and I'll have a link to that later in the presentation. But Debug Write is such a useful debugging tool, even though it's a hidden gem, I felt I had to include it in this presentation. So this is a malleable VI that adapts to any data type you wire to it to pop up a debugging window that shows you every value that has gone through that wire. If you've never heard of malleable VIs, they are a feature that was introduced in LabVIEW 2017. They're kind of like a really feature-rich completed version of polymorphic VIs. If you've ever tried to write a generic API for something that could accept multiple data types, if you did that prior to LabVIEW 2017, you probably used a polymorphic VI where you would have an instance for an array of doubles and an instance for an array of I32s and an instance for an array of U8s or whatever. You had to explicitly define all the different data types that your poly VI supported. A malleable VI, you don't have to do that. It's the same concept in terms of using the API. You can wire in whatever type you want, but the malleable VI is going to automatically adapt to whatever type that was wired in. So that was the perfect technology to use for Debug Write, which is a really quick single VI drop-in tool for debugging and seeing a history of values that have gone through an arbitrary wire type. Let me show a quick demo of Debug Write. For that, I'm going to bring back up our trusty queued message handler. Now, remember earlier, I was debugging this, maybe an issue I had with my message handling loop by doing a history probe on the message string. Well, now instead of a history probe, I'm going to use the Debug Write malleable VI. So that's all I had to do to my code. I didn't have to add any other instrumentation, just that call to that sub VI. Now, when I run the code, you'll see this debug log window popped up. And now any value that goes through that wire right there is going to show up in my debug log. And then I can scroll through and once again sort of debug and see what the history of things were that came through my debug log. If I want, I can include a timestamp on the debug log. So now when I run, I'll see a timestamp of everything that's gone through. So if I've got some timing issues, now I've got these timestamps to help me out. And the great thing about debug log is that it does give you this separate window. If you call debug log in multiple places, then you've got a consolidated place where you can see, sort of compare when things happened, especially if you're using those timestamps. And a custom probe can only be used in the LabVIEW editor. The debug log can be used in a built executable. So to summarize what I talked about in this presentation, if you want to see the history of every value that has flowed through a wire, you definitely want to use history probes. And even in cases where you've got your own custom data type that maybe doesn't match one of the default history probe types, doesn't matter. You can create a custom probe based on one of the history probes and then adapt it to your own data type. And that doesn't go just for the history probes. There's some other really useful custom probes. There's some that are used for data visualization, some custom probes for waveforms, for example. You may find that you want a customized way for viewing waveform data that's different from the way that the custom probe is that ships with LabVIEW. You can still use those LabVIEW custom probes as a starting point for writing your own. I mentioned retain wire values, probably one of the most useful debugging features because it allows you to probe wires after the fact. And then I mentioned the suspend when called feature, which is, like I mentioned, a lot of people don't know about it, but when debugging sub-VIs, it's a great way to have the code kind of stop and have the opportunity as the LabVIEW programmer to go in and manipulate how the sub-VI executes, or not how it executes, but what it does with different inputs, and then have it return a completely different output altogether, just so you can continue moving forward with your main VI. I showed the event inspector window, which is very handy for debugging the event structure. It allows you to see a log of all the events that have been handled by that event structure. It allows you to see when events are being queued up. And finally, I talked about Debug Write. Now, I mentioned that it can be used in a built-exe. If you have watched my previous LabVIEW troubleshooting presentations, you are familiar with what I call the App Builder roulette wheel, which is a series of checkboxes in App Builder that sometimes you need to fiddle with to get your exe to build, particularly when using problematic features. Remember, Debug Write is a malleable VI. Malleable VIs are one of those problematic features I talked about before. But the Debug Write malleable VI will pop up and display in a built exe, but you may have to go switch on and off some of those checkboxes I mentioned about in App Builder in order to get the exe to build properly. So watch out for that. And at the end of every one of my troubleshooting presentations, I have homework for the viewer. Your first item of homework is to go download the slides and the demos at bit.ly/dnetlvtroubleshooting. And the second bit of homework, if you haven't watched it before, or if it's been a long time since you have watched it, please check out my Hidden Gems presentation at ni.com/hiddengems. In that presentation, I talk about Debug Write, but I talk about dozens and dozens and dozens of other extremely useful features, not only for debugging, but just for application development in LabVIEW that ship with LabVIEW, but are not necessarily documented or in the palettes and quick drops. So definitely check out Hidden Gems to learn more about Debug Write and all those other hidden features as well. That's all I have for today. Thank you for watching this presentation, and tune in for the remaining presentations in my LabVIEW troubleshooting series. Thank you.